And one person who I can also call a good friend is Asokan. He is a professor affiliated to Waterloo, Canada, and I think I asked him on the chat. Still, maybe with Helsinki. He used to be at Helsinki University. I know Asokan for many, many years. He's also a pillar of our community, a long-standing pillar of our community. He has been with Nokia Research also for many years. And since then, we are working with each other. And he has a number of seminal works published specifically in the area of system security, mobile security, hardware assisted security, secure computation. And so it is a long list of influential works. And I know that he's a very busy man. But since we are all busy, we could find a slot for him in this workshop, or this workshop as a series of workshops that we are organizing. And so now he's going to talk about hardware-assisted runtime protection. So Asokan, the stage is yours.
Thank you, Ahmed. And whenever Ahmed says, "I hope I'm not insulting," I start to worry because there may be an insult coming. So let me start by share my screen. I hope you're able to see this.
Yes, we see it.
Okay, thank you.
Yes.
Yeah, so like Ahmed said, I'm going to talk about hardware-assisted runtime protection. And like he said, my primary affiliation is with the University of Waterloo, but I also retain a position, not at the University of Helsinki, but at Aalto University, which is a different university in the same capital region of Finland. As with any professor, any work or any talk they give is contributed to a lot by current and former students. I want to acknowledge my current and former students who helped me put together this presentation. So the focus of this talk would be hardware-assisted runtime protection, but particularly the tension between achieving state-of-the-art security and worrying about deployability. And this is sort of harking back to the discussion you just had earlier about standardization and state-of-the-art security. And that this is always a tension, like how do you get the best possible security, but if you can't deploy it, and if you care about deployment, then state-of-the-art security is useless. And I want to essentially tell you a story of this tension in the case of thwarting runtime attacks. So I think this audience, people in Darmstadt, and I'm sure people in Huawei know a lot about runtime attacks. I'm not going to, normally when I give this talk, I give an introduction to runtime attacks. I'll keep that brief. But I don't think this audience needs convincing that runtime attacks are routine. And many people have come up with many defenses, software defenses, and as well as hardware defenses. And software defenses, there's this inherent trade-off between security and the performance overhead. And there have been this endless array of solutions that were proposed, which try to give sort of coarse-grained security at a reasonable cost. And then someone like people in Ahmed's group will break that and show that that defense is useless. So this sort of makes hardware defenses attractive because hopefully it could sort of strike this, avoid this trade-off and say, if you manage to deploy hardware, then you can get good enough protection without the performance overhead. So I want to describe two lines of work that we did in this direction. The first one is Hardscope, which is actually a collaboration with Ahmed students. And the second is a pair of work called Paths and Packstack, which is actually a collaboration with your Huawei colleagues in Helsinki. But I'll also talk about sort of current and future directions if we have time. Like I said, I won't spend a lot of time on sort of describing the background, but just for completeness, I'll just run through it quickly. So we are talking about, when we say runtime attacks, we are talking about attacks that arise because of this widespread deployment of software that are written in memory-unsafe languages like C and C++. We all know that they suffer from various memory-related errors like overflows and use after free type of space and time-related memory attacks. And when an attacker tries to exploit these vulnerabilities to subvert or compromise program behavior, that's what we mean as a runtime attack. And there are many examples of runtime attacks, like control flow attacks and return into programming and so on. So just to set the stage, so think about like a small example like this. There's a code fragment here, and on the right, there is a control flow graph that corresponds to this code fragment. So a control flow graph is a graph where the nodes are straight line blocks of code, and edges are transitions from one such node to another node. So function calls and function invocations would be, and returns would be edges in this graph. So there's a full program, and this fragment is what is shown here as nodes 1, 2, and 3. And the way programs are compiled and run, if there is some vulnerability somewhere in the program, then the attacker would be able to use that to exploit the behavior of the program. And the classic exploitation was called code injection, which was like more than 30 years old. The first Morris internet worm used this. And essentially that means that you exploit the vulnerability to make the program jump to some piece of code that the attacker inserted rather than returning to the place where it's supposed to. And this has been largely thwarted because there are all kinds of defenses that have been deployed for the last 2 decades, such as data execution prevention, so that writable data cannot be executed, so it will not be possible to insert shellcode. There are mechanisms like ASLR, address payout layout randomization, and so on. And then this sort of gave the story of these runtime attacks. So once defenses sort of raise the bar, attackers raise their game, and so on. So once code injection was prevented, the next class of attacks are code reuse, where the attackers don't inject code, but still try to use the memory vulnerability to change the control flow of the program. So in this case, using this bug, instead of returning to this, this location where it's supposed to, the attacker can make the control flow jump to a privileged part of the code, which the attacker wouldn't have access to normally. And the generalization of this is this return-oriented programming that I'm sure many of you know. There are defenses against return-oriented programming or control flow, compromising control flow, such as control flow integrity. And these are deployed to some extent, and then that's where you run into this trade-off between security and performance overhead. But even when control flow integrity is ensured, the attacker can now still change data, such as pointers or such as non-controlled data, like, for example, this variable that decides whether you go this path or this other path, and use that to compromise program behavior. And the generalization of this is the so-called data-oriented programming. So like I said, for this audience, I will not run through more detailed examples, but I'll sort of put this up to show that, so on the blue, you see control flow related attacks and defenses, and in red, you see data attacks and defenses that sort of involve manipulating data. And over the last 30 years, there have been advances, but also newer attacks. I stopped this at 2016 because I think data-oriented programming is perhaps the last major sort of paradigm shift, but that doesn't mean that work stopped at 2016. There have been since then many papers in attacks and defenses. So to put this in sort of a bigger context, here is a taxonomy that was originally in this SOK paper from Oakland, which is a very good resource still, even though it's like 80 years old. And my student updated this in his dissertation, where you can sort of impose some structure on this landscape, right? So you can think about the different steps that one would need to achieve in order to mount a runtime attack, such as finding a memory vulnerability and using it to violate integrity and so on. And then in each case, there are sort of different types of exploitation that can happen. And then defenses are meant to thwart those. So essentially, if an attacker can string together a path through these different layers, there's a successful attack, and a defense can sort of intervene this by deploying one or more of these mechanisms. And there have been many different types of defenses, starting from software versus hardware on the one hand, and coarse grain versus fine grain on the other hand. And I'm sure many of you know about these. So coarse grain software defenses like isolation at large scale to fine grain defenses, including memory safe languages. And similarly, you can have coarse grain hardware defenses and fine grain hardware defenses where you can have a better level of protection. So the goal would be to somehow reach this bottom right corner in the interest that this would allow us to give devise protections that are sort of comprehensive without incurring performance penalty. So this is why looking at hardware systems is interesting. So like I said, I'm going to talk about two pieces of work that we did, or two lines of work, and then try to sort of tell you about the lessons learned in the process. So the first is called ArtScope, which is joint work with Ahmed students Gada and Shazar, and my students led by Thomas Newman. There's a question that says, can we download the presentation somewhere? At least my presentation is already on my website. I put a link at the top, but if you just search for my last name on Google, you will see my talks page. And if you go to my talks page, you'll see the current version of the slides that I'm presenting now. So HARDScope stands for Hardware Assisted Runtime Scope Enforcement, and I'll explain in a minute what I mean by that. So remember that we said the runtime attacks involve changing different types of data, either control data or decision-making data or other types of sensitive data. And the root cause for all of these, and this is the sort of insight that led to the work, is that it's this unintended access to unintended data from the point of view of adversary is what enables these kinds of attacks. So that's sort of maybe obvious, but reasonable explanation. The other fact is that even in languages like C and C++, at the time of compilation, the compiler will enforce visibility rules for variables. So if you declare a local variable in a function and try to refer to it outside that function, the compiler would flag an error, right? So the scope visibility is enforced by the compiler. But once compilation is done, this information is thrown away. And when the process is run, the entire memory space is sort of a monolithic object. An attacker who manages to exploit a vulnerability anywhere in the program would be able to potentially use that to change something else completely in a different place. And so the insight behind this work is that if we can somehow retain this scope information from compile time to runtime, then we would drastically reduce the threat surface for these attacks, right? So if there's a memory buffer overflow in a function, you might be able to use that to affect local variables, but you might not be able to access a variable that is not in scope of where the memory vulnerability is. But doing this has a number of challenges, right? So first of all, we said that the lexical scope is only known at compile time. So we have to have some way to instrument the compiler so that this information is retained and made available at runtime. Second is the granularity of enforcement. So there are previous works that did sort of like software fault isolation that did isolation at the level of modules. But here, what we would like is like very fine line granularity at the level of, say, functions or even blocks or even individual lines of code. The third problem is that the access depends on the context. So imagine if your subject is a function and you want to sort of decide what memory area is accessible from that function, that is not something that you can decide by just looking at the function, right? Because it depends on where the function is called, what parameters passed, and depending on that, in each invocation, a function might have access to different memory areas. And finally, like we all learned from Salzer and Schroeder, if you don't do complete mediation, then your security mechanism is useless, which means that if you want to police access to memory, you have to do this for all memory accesses. So I'll briefly explain what we did in the design and implementation and then take a step back and say, what did we learn by this? So hardscope essentially tries to instrument the program during compilation so that we identify these subjects, which we call execution context, which could be a function or a block or even like an arbitrary granularity execution context, and then associate with each subject the regions of memory that that subject is allowed access to. We call these storage regions. So in order to do this, we need a bunch of new instructions and also change the behavior of existing instruction. So for example, we need a storage region instruction that sort of accumulates these different storage regions that are accessible for each of these execution contexts. We need to track changes in execution context. So for example, when a function is called, we need to now change the subject because it's executing in the context of that function. We need to track dynamic data flows. So for example, when a function is called and a memory area is passed as a parameter, we need to make sure that that is accessible to the new subject. And then once all of this is done, then we need to change the load and store instructions so that they will allow access only if the current execution context is, has the right to access the particular storage region which the access refers to. So in all the times that we were mindful that we wanted to be able to not just do a research paper, but hopefully have people like chip manufacturers incorporate this in their design. And doing a sort of a greenfield design from scratch would be nice, but it would run into these deployable difficulties. So we were mindful of that, and then we tried to minimize the number of hardware changes that we do. So we ended up introducing 7 new instructions and changes to the load and store instructions, plus the hardware design that's needed to use these. So it's not important to go through what these instructions are, but I want to sort of point out that we tried to minimize this to 7 instructions in a whole instruction set architecture, and thought that that could sort of pave the way to deployability. Let me just give a kind of an idea of what the implementation looked like. If you want more details, like I said, my slides are available online, which give you more details. And also I'll give a reference to the actual paper, which of course describes the details and has access to the, points you to the source code and so on. So we did a proof of concept on a RISC-V processor, on a Pulpino SOC, on a Z-board FPGA. We made the corresponding compile instrumentation as a GCC plugin, and we showed that the performance overhead is reasonable. So on a standard benchmark, there's like on average 3.2% runtime overhead. There is an increase in the size of the binary, but it's also reasonable. And the hardware logic for the particular configuration that we used is also reasonable. Normally, the sort of the message I heard from talking to people in the industry is that anything in the order of sort of 10% of performance overhead is okay, 1% is even better, but more than that is starting to be unrealistic. But we thought we sort of hit that ballpark here. There are a number of benefits in hardscope. Like I said, the granularity of this execution context can be really fine. So one can do it module level. Our default implementation is function level, but one can also do it even in code block level or even narrower. The second thing is that the essential goal, or what is achieved by this, is reducing the threat surface. So it can limit the effectiveness of large classes of attacks like return-oriented programming and data-oriented programming significantly. There are some limitations. Some of them are sort of implementation limitations, which can, with sufficient resources, can be addressed. Like currently, we only support single threading. Some are more fundamental limitations, which can be addressed, but would result in like a higher cost. For example, to keep track of this access control list, essentially. So that, remember that we have an access control list that says which memory areas are accessible by a given execution context. That has to be in a secure memory, right? So the attacker should not be able to exploit a memory vulnerability to change that. we have to decide the size of the maximum size of this secure memory at design time. And that would then have an effect on what kind of programs could be supported. What is the level of nesting in function calls that would be supported? But the biggest objection that we found, both from program committee reviewers, but also from companies that we talked to, including Huawei and Intel and ARM, is that even though we had only 7 instructions, that was seen as sort of 7 too many. So after a long round, the paper was eventually published in a top venue for digital design. We have the source code available. So depending on your criteria, the student got his PhD. Depending on your criteria, you can declare this as a success. But if you care about technology transfer and deployment, then this is not so satisfying. So that's what led to us asking the question that, so how do we reach the same goal, but while avoiding these major deployment hurdles? And even sort of small hardware changes were seen as raising the bar significantly. So what do we do in this case? So the development that sort of motivates the second part of this talk is that there are some hardware-assisted defenses that are being rolled out in off-the-shelf processors by processor manufacturers. So ARM has a number of hardware primitives that they have been rolling out. Pointer authentication is already on in processors that are used by Apple. Memory tagging extensions was announced a year and a half ago, and presumably it will show up in future processors. And similarly, branch target indication. And it's not just ARM. Intel has a number of other primitives that they have announced, including one that they announced last month called cryptographic capabilities. So they are rolling out these different primitives. And as you can imagine, the kind of primitive they roll out is influenced by sort of their cost-benefit trade-off, right? So they will not roll out a comprehensively new architecture, but some small enhancement somewhere that satisfies their concerns about backward compatibility and cost and so on. And usually this is motivated by specific things. So I'll explain in a minute that, for example, pointer authentication was intended by ARM and Qualcomm for return address protection. But these are primitives, and one can ask these questions like, can we use these primitives in ways other than what was intended? What are the problems in using the primitives in the ways that were intended? And then can we combine these primitives? How do they compare to each other? Because none of them are sort of comprehensive solutions, but there is like a menu of different choices. And how do they compare? If you are a new hardware manufacturer and you want to decide which primitives to include, how would you go about choosing them? So this is what sort of drives much of our current work. And I'm going to describe 2 pieces of work that relate to this called Parts and Packstack, which uses this particular primitive called ARM pointer authentication. So the setting is, like I said before, that deploying hardware extensions, even though it's attractive, it's difficult. And that leads to the question that how can we use these mechanisms that are being rolled out by hardware vendors so that it avoids this question of like, this is too invasive a hardware change. And how can we understand the level of protection afforded by them and how they compare to each other and so on. So let me start by giving a quick overview of what ARM pointer authentication is. And I'll mention a couple of others, other primitives and which are part of our current work. So ARM pointer authentication is, the motivation is essentially to try to achieve pointer integrity. So pointer integrity is like what the name says, it's a way to guarantee that pointers in the memory remain unchanged, or rather the attacker may be able to exploit a memory vulnerability to change a pointer that's stored in memory, but pointer integrity would assure that we'll detect that. And if we can detect that, then we can take remedial action. So you can imagine how this can be used. So think about a function. In the case of ARM, if this is not a leaf function, then as soon as the function prologue is, as part of the function prologue, the return address, which is normally kept in a register in ARM, would be written to the memory because there is a subsequent function invocation that's going to come somewhere in the middle. And this is where the attacker can use a memory vulnerability to change it. But if you have a pointer integrity, then at the time when this function is about to return, we load the address from the memory, but instead of just returning it by trusting it, we will verify the integrity. And if you have a good memory pointer integrity mechanism, at this point, we'll detect that the pointer has been changed, and then we can crash or take some remedial action. So that's how it would work for return addresses, like code pointer integrity. You can imagine that you can also have similar notion for data pointers. So ARM point authentication was sort of an attempt to try to approximate this notion of code pointer integrity. And you can think of this as consisting of sort of two pieces. One are sort of new instructions that can be used to compute an integrity value, like which ARM calls point authentication code for a given pointer. And then also check that integrity value later on before you use it. ARM uses cryptographic message authentication code as the basis for pointer integrity. That means that you have to manage that key somehow. And that's the second part. So this was introduced in the ARM specification version 8.3, and they have been continually improving it because there were some attacks that were discovered in the meantime. Apple processors are the ones that have deployed it so far, but there have been software support for it in Linux kernel and GCC and LLVM and so on. And the high-level idea of how this works is that for user space key management is done by the operating system. The operating system sort of picks the keys, one per processor for every time a process is started. And when the process dies, the key goes away. And if you start the same process, same application again, it'll get a new key. So just to give you a quick idea of how this works. So in any architecture, including ARM, you use full words for representing pointers, but you don't actually use all the space in the word for the pointer because the addressable memory is usually limited. So in the case of, say, Linux, it's usually 2 to the 40 bits. 40 bits are enough for the address, but the word is 64 bits, so the remaining bits are unused. And the idea of pointer authentication is to compute a message authentication code on this address using a key that is managed, like I said before, and put the resulting message authentication code in these unused bits. So note that this is necessarily going to be short because the number of bits that are available is something like 16 to 24. So it's not going to be like a full standard cryptographic strength MAC, but it'll be a short MAC. The other thing is that this is not a simple message authentication code, but what cryptographers call a tweakable message authentication code, where in addition to the plain text input and the key, you also take a tweak as a parameter. So the way to think about this is that if you think of message authentication code as a mapping from an input space to a fixed length output space, you can think about a tweakable message authentication code as a family of such mappings where the family is induced by the tweak, right? So the tweak doesn't need to be secret, but by changing the tweak, you can change the mapping. And the idea is that you can sort of make this tweak represent the context so that you will be effectively using different message authentication codes in different contexts, even though you're using the same key. So once you have a primitive like that, basically you have, if you want to build a protection scheme, you have to answer 2 design questions. First is when are you going to compute this message authentication code, which ARM calls point authentication code in this case. So when are you going to pack a message of the pointer and then unpack, which means verify that. And then what is the modifier you are going to use at this point? So of course you could use the fixed modifier, but that would mean that the whole process while it's running will use a single message authentication code. And remember that the size of the MAC is small, so that's sort of a motivation to bind the context so that at least you minimize the use of a key or use of a certain mapping within the program by limiting, by isolating different contexts using different modifiers. So intuitively, you would think that the modifier should be unique for every pointer. That would be the best case, right? So every pointer has its own mapping. But there's a trade-off here, right? So for security, you want to make it as unique as possible. But remember that the modifier should be available both at the time of packing and at the time of unpacking. And you can't use something like a nonce, because if you use a nonce, you have to store it somewhere. And you have to store it in a way that the attacker cannot modify. If you have a way of securely storing something, then you might not even need point authentication in the first place. So that's the second thing. So you need to find a modifier that is sort of naturally available at the point of packing and at the point of unpacking, but as unique as possible. So the original intent, which ARM and Qualcomm did when they designed this, was for return address protection. And the way it worked is like this. So consider this function that has, in the prologue, it stores the return address. So in ARM, the LR is the return address register. If this is a leaf function, then this instruction will not be there because the return address will just stay in the register. But if it's not a leaf function, if there's another function invocation here, then we have to free up this register so that the child function can use it. And that's why the function prologue will write this register to memory, which is where the attacker could change it. So this is the big picture that I showed you before when I talked about pointer integrity. So what we need is a way to set up some pointer integrity mechanism here so that when we finally load this return address to the LR register, and before we jump to the place using that register, we verify the pointer integrity. And ARM does this, Qualcomm proposed that they do this using point authentication code by using the stack pointer at this point as the modifier, and then computing a key. PAC allows, point authentication allows sort of 5 different keys for each process. And this particular key is called IA key, which means the A key for instructions. There's an A key, there's a B key for instructions, and then there are 2 keys for data, and then there's a general key. So there are 5 keys in for each time you create a new key, it's actually a set of 5 keys. So it uses the IA key and the return address and use the context as the stack pointer as the context and put these back there. So the idea now is that if the attacker modifies the return address, he is no longer able to arbitrarily change the address because he doesn't know the key, and therefore he wouldn't be able to modify the pack. At the time of loading, we will invoke this verification instruction, which now uses the same modifier. Remember that we don't have to store this stack pointer anywhere because that's naturally available at this point. So we can instrument this code so that we recompute the pack and check if it's what's in the map. And the actual point authentication has sort of a whole bunch of other instructions. So for example, you don't need to do auth IA and ret separately. You have an instruction that does both of them together. So if you haven't seen this before, you're probably already sort of thinking about this pack reuse. So I said that the attacker won't be able to create a new pack for an arbitrary address, but of course they can harvest old return addresses and old packs, and then you try to reuse it. So here is an example of how that might work. So think about a function, a scrap of code like this, where at some point you call function 1. So the actual instruction might look like your branch to the position of function 1, and then sometime later you call function 2. So when we use this Qualcomm mechanism at function 1, in the prologue of function 1, we would compute this point authentication code using the stack pointer, and that's what would be verified. But the attacker can now steal this point authentication code. And then when function 2 is invoked, he won't be able to insert an arbitrary return address, but he can replace the previous return address for function 1 and just replace it here. And this is going to succeed because the stack pointer would very likely be the same when both of these functions are called. So even though arbitrary control flow changes are not possible, this kind of control flow change would be possible. Like when from function 2, we would return back to function 1. In this case, that's not directly a vulnerability, but you can imagine that this could be exploited by the attacker. So in parts, we looked at this return address signing and how to sort of tighten this. But we also looked at how we could use same mechanism because it's a primitive how could we use for other things, such as not return edges, but forward edge protection, so generally code pointer signing. How do we protect data pointers? For return addresses, we essentially tighten this potential for reuse by not only using the stack pointer, but also the function definition. So, for example, LLVM has a notion of a function type, and data pointers have a similar notion of a data type, and we can bind that. This doesn't eliminate the potential for reuse, but it sort of reduces the gap. So this is something that we presented in Usenix Security a couple of years ago, and there's a link to the paper. The source code is available, so on. So the next thing is the second piece of the work is sort of thinking about this, reducing this scope. So earlier I said that ideally you want a unique modifier so that there will be no other place where that modifier is used. And it can't be a random nonce, because then we have the problem of storing the nonce somewhere. So we asked the questions like, what could we do in the case of return address protection so that we can make the modifier as unique as possible? So a stack pointer is certainly not unique, because there could be two different function calls that could occur at the same when the stack is at the same place. So the intuition here is that a unique characterization of any given function call is the entire call chain at this point, right? You can't go any more unique than that. So if we can somehow capture this call chain and then use that as the modifier, then we would our protection would be optimal. We can't do better than that. So once you have this idea, then the solution is sort of straightforward. We use this pack not just to compute message authentication code for the current return address, but we include the entire call chain before that as a modifier. So the way we would do that is initially we would use a fixed modifier like 0, but then the next time we compute the next function call, we'll take the next return address, but then use the previous authenticator as the modifier. So that at any given time, the chain of message authentication codes actually represent the call stack. So as long as we protect the top of this chain, for example, in a dedicated register, the attacker won't be able to change any of these without being detected, because if the cryptographic hash function is a good function and is free of collisions, and then any change would result in a change in the value that we store, the reference value that we store in a register. So that's a simple idea. There are it prevents reuse, and it allows precise verification. There are a couple of subtleties. I'll just give you an idea about one of those, but let me refer you to the paper for details. The MAC is short, so if you don't do anything else, then birthday paradox will come into play. For a 16-bit MAC, if you have 321 addresses, there will be a chance of a collision, right? The MAC would collide. And 321 addresses, harvesting that isn't out of question. So the way we deal with this in this pack stack, which is the Usenix security paper that we presented earlier this fall, is to use the same message authentication code mechanism to create a mask that would, so what we store on the stack is not just the pointer with the MAC, but with the pointer and the MAC masked with another run of this message authentication code. What that does is to prevent the attacker from being able to recognize that there are collisions. And we can show that this gives us the best possible protection. It is still limited by the number of bits, but we can, let's say that if you have 16 bits, then the statistical protection you get is 2 to the minus 16. And before you sort of wonder why this is enough, remember the way this works. Each process gets a key. That key is alive only during that process. And if there is a pack failure once, then the process would crash. So effectively, the attacker gets one guess. There are a couple
just to let you know, 5 minutes left, just to let you know, 5 minutes.
Yeah, I will be done in 5 minutes. Okay, so so there are subtleties in doing this as well. So I want to just quickly tell you about a couple of other extensions that are coming and that are the basis of some of our current work. The second one is memory tagging extension, where in ARM, you can associate a tag, 4-bit tag. So think of it as a color. Whenever you do a memory allocation, you can associate the color with the memory allocation and also with the pointer. And then the basic idea is that a pointer access is allowed only if the colors match. If you free a memory allocation, then you randomly change the color of that allocation so that any dangling pointers won't work. So use after free would be prevented. So this is already, there is support in LLVM for some of this. There is no hardware yet that has this. I apologize for the background noise. Somebody in my building is vacuum cleaning the corridor, but bear with me. Like I said, there's already software support for this. Uses 4-bit tags. And there's already protection systems that make use of this. So LLVM, Memtag Sanitizer make use of this. They use randomized protection so that the tags are assigned randomly. So essentially you get this 0.94 chance of detection. If there is a mismatch accidentally, then 94% of the time you would detect it. But this is intended as a developer tool. While you are developing code, you identify problems. But the tags are corruptible. The address tag is in the pointer itself. So the attacker can go and change the pointer. So because of these reasons, you cannot really use this as an enforcement mechanism for post-deployment. You can use it as a developer tool. But in the standard adversary model for runtime attacks, where you assume that the attacker has full access to the memory, things like Memtag Sanitizer aren't effective. So this is the question we ask now, like how can we use MTE to provide post-deployment runtime memory safety, given that the straightforward use is not feasible? So I'll not talk about branch target indication. That's another thing that ARM is rolling out. And just for sort of to visualize these, so these things address different aspects of this, different attacks that an attacker could use. And that's how they thwart this, possible attacks. So I want to leave you with sort of one thought. So if you have these different mechanisms, the natural question is, how do these compare? So we can, for example, compare the return address protection using point authentication versus the use of hardware-assisted shadow stacks like Intel has in their CET technology. So here is a quick comparison. They are both intended for return address protection, but I told you that point authentication is a general primitive, so it could be used for other things than return addresses. Shadow stack is a deterministic mechanism, so there is no probabilistic protection. Whereas in ARM, there is this element of accidental match. This is mitigated by the fact that we can make it as optimal as possible, and we can also, the attacker gets only one guess. So I think there's a fruitful line of research looking at these different mechanisms and how they compare. And this is just one attempt, but you can also combine these in different ways. And in this case, I think the comparison is really hardware-assisted shadow stack is a custom solution. Point authentication is a generic building block, but it comes with this caveat that it is probabilistic protection. And you can think about what else you can use it for. So in addition to the two things that I told you about, we have used it for strengthening stack canaries. There's also a student of mine is currently working on data structure protection, because point authentication is essentially a hardware-assisted MAC. So how can you use it to provide a library that gives you an authenticated stack or an authenticated tree or authenticated queue? So these are the possibilities that come because it's a generic building block. So I'll stop here. And just to summarize, there are new hardware-assisted defenses that are being rolled out. And therefore, it's interesting to ask, how are they intended to be used? What are their downsides? How can we address those downsides? Can we use it in novel ways? And how do these things compare? The underlying big thing, which we don't have expertise in, but I think this is something that is also a fruitful line of research, is how do we formalize this? How do we sort of break out of this arms race so that we can understand the level of protection that is given by any defense mechanism? So I'll stop here, and if Ahmed thinks that there is time for questions, I'll be happy to answer your questions.
Of course. We don't invite Master Asokan and just stop after his talk. So is there any question? Okay, I see many people in the thing. I can pick one. Asokan, you also see the list of participants. Do you want to ask someone?
Should I do like in a classroom?
Yeah,
exactly. At somebody.
Our job. This is our job. We go to classroom and ask someone, and they try to not to hide themselves. So, so if
I'd like to ask a question.
Oh, yep. Perfect. Yeah. We have a winner. Please go on.
Hi, Professor Asokan. I'm a PhD student with Huawei. So I'd like to ask that, as you mentioned, that for pointer manipulation or for memory safety, you are looking to formalize this. So would one possible way to look at this would be to use maybe separation logic to be able to?
It is possible. So like I said, I'm not an expert in this, so I can't sort of give you a definitive answer. The formal methods community has made sort of big advances, for example, in protocol analysis. But in system security topics like this, I think it's still limited in the sense that a practitioner doesn't have easily available tools to, like if somebody in Qualcomm or Huawei designer memory safety mechanism, my understanding is that there is no easily available tool or even sort of a methodology that they can apply routinely. In this particular paper, the paper on PackStack, my postdoc who is familiar with cryptographic proof mechanism essentially used a cryptographic approach, essentially showing like a game-based approach to show that our scheme is secure. What I can say is that I think this is a fruitful area for people who are specialists in formal analysis, because there are tons of defenses and attacks, but the formal analysis or formalization is lagging behind.
Okay, but would game-based proofs and all these cryptographic proofs be useful here to check for pointer manipulation, or would you want to go more towards more process algebraic approach or program logic approach?
You're right. So I think the cryptographic techniques are applicable in limited settings. So in our case, we use this to show that the reuse attacks, the protection that we provide against reuse attacks is optimal, right? So if you have 16 bits, then you get 2 to the minus 16 level of protection. That doesn't say anything about all the other attacks that would be possible based on, I don't know, side channels or whatever, right? So you would need a more comprehensive approach. Cryptographic techniques would apply to parts of these, like we used.
Okay, thank you.
Thank you. Any other question? Okay, so currently I don't see any hands raised, and okay, Asokan, thanks a lot. But maybe as a last question, what is so you put some takeaways, but what's next? So we heard here today the talk by Serjan, where we saw that, for example, you want to create secure containers and kind of having a trusted execution environment so that you have the user has the control over it, which I think in practice, of course, this is a debate that we are going to have with Serjan as well, that in practice things will be completely different than when users have this trusted execution environment. But this is from the user has control. But now in your case, you have a system against some runtime attacks. Now, what would be the future? Do you think users can have a trusted environment that it's under their control, and since it is under their control, it may not be protected so well, And so we need more fundamental protection there as well, and who's going to manage it? So what will be the future of this? So because this is not the last line of defense or last work that you have done, there are still things missing. And what are the missing points? And would a user be able to have such a compartment for him or herself?
Right. So I was fast asleep when Surgeon gave his talk, so I wasn't there. But I think we are talking about sort of two orthogonal things, right? There's this debate about trusted execution environments, and is that, what do we do when that's working against the interests of the user? But now in this case, and that's something that I'm interested in, and I think there's like pros and cons about what kind of user control is it effective and so on. But here we are talking about software vulnerabilities, and these are independent of whether there is an isolated environment or not, right? So you can have the same kind of software vulnerabilities within a trusted execution environment, within a sort of enclave, or you can have it separately. So I think the question of user freedom doesn't arise here, right? So these are vulnerabilities, we want to fix them, and I think, I hope that everybody would agree that these should be fixed, because this can only harm the user. That there's no benefit in users to keeping them around. The only people that I think would want to keep this around are people who want to weaponize these vulnerabilities as a way to attack users' devices, right? And this, as you know, includes not only the bad guys, but also the good guys, because the good guys want to weaponize vulnerabilities because of exploit protection. So I don't think that tension of like, do we need user control arises here, because that arises in this case where you have an execution environment that would provide guarantees even to some third parties about your platform, and that might be used against you. In terms of next steps, I think there are clear short-term next steps, and there's like I said, it's a fruitful area of research because these new primitives are being rolled out. So even though it doesn't solve world hunger and world peace and whatever, it looking at these individual pieces of research and then individual pieces of hardware primitives and thinking how they can raise the bar in a way that is both provide you fine-grained security without high overhead and without this question of deployability. I think this can keep lots of PhD students busy for the next little while. That doesn't answer a question like that. The visionary like you would ask, like, what's the big picture of it?
The first question that, my first question that you, so you answered in the sense that maybe I express it again. So if you have a compartment, if you have an environment on your mobile phone that is under control of the user, and you still have all these software vulnerabilities that is independent of, as you correctly mentioned, independent of this trusted execution environment. So the user will be a good, so to say, a good target for these attacks as well. Now, to protect against these attacks, again, in turn, we need to add approaches like your approach to the hardware or to the software, or a combination of that, hardware, software, co-design. And again, that because this user control idea is that providers or big corporations do not have access to anything. But however, to guarantee the security of the user, again, the vendors and big corporations are coming in. So my question is, the user cannot do this complex approach that you have been doing, that these experts view and researchers view. And again, companies and corporates will put mechanism in those systems that users are protected, but then they are coming back to this user compartment. So we cannot get them out of this compartment. That's what I was saying. That do you see any possibility to get them out of this?
Right, but I think it's maybe unreasonable for a user to say, I want to run my my device because I want to, this is like, I don't know, anti-vaccine or something like that. I want to have freedom of choice, and therefore I want to leave these vulnerabilities inside. I think a legitimate user concern would be, how can I stop a device from being used against me? But here we are talking about vulnerabilities that can be used to harm the user. Yeah, it is true that it's the operating system manufacturer and the hardware manufacturer who can deploy these mechanisms. The user can't do that by themselves, but these are to ensure the safety of the user, right? So,
yeah.
So maybe an analogy would be like an antivirus.
Yeah.
Right? So antivirus is not taking the freedom away from a user, because without the antivirus, you're going to be in trouble as a user. So
exactly. So okay. So you see it kind of as I see it. I see that Mark Stottinger has his hand raised. Please, Mark, go on.
Yeah, Asok, thank you for this wonderful talk. My question is, how do you see the impact of this runtime protection schemes with regards to testability of chips and hardware? I mean,
right.
Testability is quite complex. When you have field returns, you have sometimes ugly situation that it's a combined failure of software and hardware.
Right. So that is an interesting question. So not only testability, but also this kind of triaging, right? So what happens when a process crashes because there was a point authentication failure? If an attacker, so remember that there was like the 16-bit field, right? So if an attacker is attacking 100,000 Android devices, he's going to succeed in some of them, right? And that we can't protect unless we have a long enough message authentication code. But what we can do is this kind of telemetry that if an attacker is attacking large number of devices, he's going to succeed in 1 every 2 to the 16. But before that, there will be point authentication failures in the remaining 65,000 devices. And if this telemetry goes back, and if there's a way of triaging this, then somebody like Google could, or somebody like Huawei could take action against this. You know that a particular application is failing in multiple devices because of a point authentication failure. So not only during sort of field return testing, but also like in deployment, there's a lot of work to think about, like how do we make use of these? Right now, all we have said is that we can protect the user in case there's an attack by crashing the process. But you want to protect users at large, and that will involve some way to sort of gather this information and act on it. Like, for example, recall a program that is vulnerable, or prioritize in the triaging process, prioritize the debugging of that application that is failing because of a point authentication failure. Did that answer your question? Or?
Yeah, thanks completely. Thank you.
Super. So Asokan, we really want to ask you more questions because it's very early at your time. You have time.
It's not that early. It's 11 o'clock.
Okay, 11 o'clock is academic, very early. So I would like to then close this session with Asokan.